This is cylindrical rotor type synchronous machine, and this is Salient rotor type synchronous machine. This is stator frame, stator core, and this is rotor core, and this is slot in rotor to house field winding, and DC supply is given to the field winding. Here this is rotor core, this is rotor core, and this is stator core, this is armature winding, and this part is air gap. This is also air gap, this is air gap, and here we will have field winding. Current is coming out and here going inside. So here also the direction of field flux will be upward. In both the machine, direction of field flux is in upward direction. And consider in a stator slot there is one armature winding. Just for analysis, consider only one armature winding here and one armature winding here also. Now, if we talk about air gap, the air gap between a stator frame, stator core and rotor core is uniform throughout this periphery, where in case of Salient rotor synchronous machine, the air gap at this point, air gap is minimum, and if you move away from this point, air gap is increasing, and here in this position air gap is maximum, and this is the direction of field flux. In the direction of field flux, we will define axis. In this direction field flux is maximum, this is the direction of field flux. So to this axis we will define this is D axis, and to perpendicular of D axis, this axis will be Q axis. Here also this is the direction of field flux, so this is D axis, and this is Q axis. Now suppose rotor is rotating in anti-clockwise direction. Here also rotor is rotating in anti-clockwise direction. So this field will rotate in anti-clockwise direction with respect to this conductor, or we can say that the relative to the flux, the conductor will move to in clockwise direction. So in this position, the velocity, the direction of velocity of conductor will be in the right direction. Relative to the flux, the direction of velocity of conductor is in right direction, and the direction of flux is in upward direction. This is B, this is V. So direction of V cross B will be outward. So the positive charge in this conductor will experience force in the outward direction. So the direction of current will be in outward direction. Now before analyzing the current, we will say that this conductor, the direction of flux is in upward direction. So this conductor is completely in the influence of north pole, or this conductor is in the maximum influence of the field flux. Here also this conductor is maximum, this conductor is the influence of maximum field, because if this will rotate, the field axis will rotate and it will get a cos component of the field. So we will say if this conductor is in the maximum influence of the field, so it will have maximum EMF generated. In this position it is in the maximum influence of field. So this conductor, and here also this conductor will have the maximum EMF generated in it. Now EF in this conductor is maximum, it doesn't mean at the same instant the current will also be maximum. If the EMF is maximum, but current, the instant of current at which the instant of time at which the current will be maximum, it depends upon the load. If there is a lagging load, so the current will lag EMF. It means the maximum value of current will lag the maximum value of EMF, or the minimum value of current will also lag all the values of current will lag all the corresponding values of EMF. So, if a lagging load is connected here, the instant of maximum value of current will lag the instant of maximum value of voltage generated in this conductor. So, let us say a lagging load is connected to this connected as a load to this generator, and suppose the lagging angle is 45 degree. So, if at some instant, at this instant voltage is maximum, so current will the instant of maximum value of current will occur after 45 degree, and in the 45 degree this rotor would have rotated anti-clockwise by 45 degree. So, we will say the field axis would have rotated. This was the initial position of field axis when the EMF in the conductor was maximum. Now, the field has rotated by 45 degree. The field has rotated by 45 degree, and after 45 degree current in this conductor is maximum, because a 45 degree lagging load is connected to this conductor, this generator. So, at this instant the current is maximum. So, at the same instant the MMF due to this current will be maximum. And what will be the direction of MMF due to this current? The current is coming outward. So, the direction of MMF will be in this direction. So, this is the direction of MMF, armature MMF. We will say this is the direction of armature MMF, and this is the direction of field MMF. If resistive load is connected here, so the maximum value of current will occur at the same instant when the maximum EMF is generated in this conductor. So, and maximum EMF will be generated in this conductor when this conductor is in the maximum influence of the field. So, if the position of field is in upward direction, the conductor will link with the maximum field. So, maximum EMF will be generated, and if load is purely resistive, unity power factor load, so at the same instant maximum current will be induced in this conductor. So, the armature MMF will be in this direction. So, the orientation of two MMF will be like this. If we have purely lagging load connected to the generator, purely lagging load means maximum of IA will occur 90 degree after the maximum of EF. So, maximum of EF occur when the field in this position, when the field flux is in this direction. And what will be the 90 degree after duration? After 90 degree, the field flux will rotate 90 degree it will rotate by 90 degree electrical angle. So, the situation will be field flux would have rotated by 90 degree with respect to its initial position, and now current in this conductor will be maximum. So, the armature MMF is in this direction. So, the two MMF are in we have already done this exercise. If the current is purely lagging, the two MMF will be opposite to each other. If the current is of unity power factor, the armature MMF will be cross magnetizing, and here a general lagging current. In case of general lagging current, a part of armature MMF will be opposite to field MMF, and another part will be cross magnetizing. This angle is, instead of 45 degree, we will take this angle as psi, the internal power factor angle. So, up to here the analysis is same for salient type machine and cylindrical type machine. Now, in terms of MMF, the analysis is same, but if you try to analyze in terms of armature flux, the analysis will be different. Now, we will try to analyze in terms of flux. If we try to analyze flux for this case, the maximum current will be induced in this winding when the rotor has rotated up by an angle of psi. So, let us rotate it by an angle of phi. So, these positions, this rotor would have rotated phi angle in anti-clockwise direction. So, this part will come here, and this will be like this, and these two conductors will come here. Now, the direction of MMF is, this is the direction of armature MMF. So, now flux is equal to, armature flux will be equal to armature MMF divided by reluctance. So, there will be some magnitude of armature flux, and we also know that in the path we will have reluctance of core, reluctance of air, and reluctance of core, but reluctance of air is very high if we compare it with the reluctance of core. So, the total reluctance will be dominated by reluctance of air gap. So, the reluctance will be decided by the width of air gap. Now, instead of this angle psi, if the rotor was rotated some other angle, let us say 90 degree, these two conductors would be here and this part of rotor would be here. So, even if any position, if rotor has rotated by any angle, the air gap MMF would be same, and the maximum armature current in this conductor will have a definite value of maximum armature MMF, and the air gap is always fixed. So, the reluctance, irrespective of the orientation of rotor position, does not matter by how much angle rotor has rotated. The air gap in the path of armature MMF is always fixed. So, the reluctance offered by air gap or the reluctance offered in the path of armature MMF is always fixed. So, in case of cylindrical rotor machine, synchronous machine, the value of armature flux due to armature current is always fixed. It does not, I will write a statement here. In cylindrical machine, the magnitude of armature flux or the magnitude of maximum armature flux, maximum phi A, does not depend upon rotor position. And how we decide the position of rotor with respect to the maximum current? It is decided by the power factor of the load. because the instant at which the maximum current is induced in this winding, it depends upon the power factor of the load. So, we can say that the maximum armature flux or the armature flux, because the RMS value of armature flux will be maximum divided by root 2. So, the value of armature flux does not depend upon the power factor. So, it is fixed. Whether it is demagnetizing and how much it is demagnetizing or cross magnetizing or magnetizing, that will depend upon the power factor, but the value of armature flux does not depend upon the power factor. But in case of, if we analyze the same thing in case of salient rotor machine, what will happen? Suppose the load is 45° lagging, or the load is unity power factor. This is the case of unity power factor. This conductor is in the influence of maximum field. So, maximum EMF will be generated, and since power factor is 1, so at the same time maximum current will be generated. So, corresponding to maximum current, we will have maximum armature MMF in this direction. Now, the maximum armature MMF is in this direction, but in this situation the rotor has this position. This armature will have to face this much air gap. So, in unity power factor case, the maximum armature flux will be the maximum armature flux phi A max is equal to F A max. The value of F A max is fixed. Reluctance, this reluctance will be, this is Q axis. So, this is reluctance along Q axis. Now, if we analyze the case of purely lagging load. So, what will happen in case of purely lagging load? If rotor is in this position, maximum voltage will be induced in this winding, but the maximum current will be induced after 90° after the maximum voltage has induced in this winding. So, the current will be maximum after 90°, and after 90° the two poles would have rotated by 90° in anti-clockwise direction. So, MMF due to this winding will be maximum when the rotor position will be along Q axis. We will have this kind of rotor position. In this position, the current in the armature winding will be maximum, and this will be the direction of armature MMF, and this is the direction of field MMF. Now, this point will come here. So, this is stator part. So, now the same MMF, the same maximum MMF, because the same maximum armature current will be induced. So, same maximum MMF will feel reluctance of due to only this much air gap. So, in this case, this is unity power factor case, and the maximum value of armature flux will be the same maximum MMF, this is same, but now the reluctance will be D axis reluctance. This is D axis. If the rotor is rotating, along with the rotor D axis will also rotate. So, this is D axis reluctance, and reluctance along D axis is less than reluctance along Q axis. So, with the same maximum armature current or with the same maximum armature MMF, if power factor of load is different, then the maximum armature flux is different. This is for purely lagging load, and this is for unity power factor load. Similarly, the load may have, the load has many variety, or depending upon load, the power factor may have, means various power factor load may be connected, and in all the cases the value of armature flux will be different, because for different load the maximum armature MMF will experience different air gap. Suppose the load, the power factor angle is 35 degree. So, maximum armature MMF will experience, or the maximum current will induce in this winding when the rotor has rotated 35 degree in anti-clockwise direction. So, if it is rotated 35 degree, this may be here, and here the air gap is this much. So, in all the cases air gap will be different. So, in all the cases the reluctance offered by to the MMF will be different. So, the armature flux will be different in all the cases. So, but if you come to the cylindrical rotor machine, the maximum value of armature flux is always same, because in any rotor position the air gap is always fixed. So, if we analyze in terms of flux, the flux will be different in case of Salient type machine. Okay. Now, from armature flux, to see the effect of armature flux in the circuit diagram. So, first I will draw the circuit diagram. We started with this type of circuit diagram. This is generated EMF in case of cylindrical machine, and we will in similar way we will try to develop circuit diagram for Salient rotor type synchronous machine. This is generated EMF due to field flux only, but if current will flow there will be armature reaction, and to take the effect of armature reaction there will be armature flux, and due to change in armature flux a voltage will be generated, and the magnitude of voltage will be directly proportional to the magnitude of armature flux, and magnitude of armature flux is directly proportional to armature current. So, overall we can say the magnitude of voltage is directly proportional to armature current. The effect of this is the effect of changing armature flux. So, the effect of changing armature flux is directly proportional to armature current. So, this voltage is directly proportional to armature current, and the constant is, and the phase difference between the voltage and current is 90 degree. So, V can be written as, this is effect of armature changing armature flux, this is J, and the constant is XAR into IA. So, here we will show a voltage drop since the current is IA. So, this reactance is JXAR, and there will be some voltage drop due to changing leakage flux, and this is also directly proportional to IA. So, same IA will flow in the leakage reactance also, and here we will have terminal voltage. I am neglecting armature resistance. If armature resistance is there, so we will again add armature resistance, and here we will have generated EMF due to resultant flux. Resultant flux is the combination of field flux and armature flux. But the same circuit model is not applied to Salient types, Salient rotor machine, because the value of armature flux depends upon the power factor of load, or it depends upon the orientation of rotor. And for different orientation of rotor, the reluctance provided by the path is different. So, the flux is different. So, we do not have a fixed flux irrespective of the power factor. So, this circuit diagram of synchronous generator is fixed irrespective of the power factor of load, but here flux depends upon the power factor. So, this reactance will depend upon the power factor. So, the same circuit is not applied, and there may be infinite type of load. So, for different load the power factor angle will be different. So, the position of rotor to the maximum armature MMF will be, the number of position will be infinite. So, to analyze what is done, this armature MMF is resolved in two directions. The one direction is along D axis and the other direction is along Q axis. The two axes are perpendicular to each other. So, armature MMF can be resolved in these two axes, because with the movement of rotor, with the rotation of rotor, the D axis is also rotating. So, we can say that, and along D axis the air gap is fixed. So, we can say that the reluctance along D axis is fixed and reluctance along Q axis is also fixed. So, it is better to resolve the total armature MMF in along D axis and Q axis if this is the total armature MMF. And suppose for a psi power factor, this was the maximum EMF position of the rotor. In this rotor position, the EMF generated in this conductor was maximum, but the load is phi angle lagging. So, after phi angle, current in this conductor has reached to the maximum value, but after phi angle the rotor was rotated phi angle. So, this is the rotor position and current in this conductor is maximum. So, armature MMF in this direction is maximum, and this is the D axis, this axis is D axis and this is Q axis. And this is psi. Psi is the angle between maximum current and the generated EMF, not the terminal EMF. Psi is angle between EF and armature current, maximum EF and maximum armature current, and that is what the phase difference between EF and IA. So, in this position this armature MMF is maximum, but this angle phi is different for different load. So, what is done? This armature MMF is resolved into two parts. This is D axis, this is D axis. So, one component of armature MMF, because along D axis and Q axis, this is the maximum air gap axis, this is minimum air gap axis. Along D axis and Q axis, the reluctance is fixed. So, armature MMF is resolved in the direction of these two axes. So, suppose this is the armature MMF, one component will be D axis component of armature MMF, this is FD, and other component will be perpendicular to it, this is armature MMF along Q axis. So, FA will be written as vector sum of FD plus FQ, or the MMF and currents are linearly related. So, if you divide it by number of turns or same constant, we will get we can also say the armature current is divided into two parts, ID plus IA, sorry, IQ. And what is the angle between FA and FD? This angle is psi. This angle will be 90 minus psi, because this angle is 90 degree. So this angle is 90 minus psi. This angle is 90 minus psi. So we can say that FD is equal to FA cos 90 minus psi. FD or FD is equal to FA cos 90 minus psi or FA sin psi, or we can say that the D axis current is equal to ID sin psi. Similarly, IQ, Q axis current, this is IA cos psi. If one component is sin phi, the other perpendicular component will be cos psi. So MMF along D axis is, this is MMF along D axis. So armature flux along D axis will be FD divided by reluctance along D axis. So this will be FA sin psi divided by reluctance along D axis. Similarly, flux along Q axis will be FA cos psi divided by reluctance along Q axis. And total flux, armature flux, can be again written as flux along D axis and flux along Q axis. Flux along D axis plus flux along Q axis, that is FA cos psi, FA sin psi divided by reluctance along D axis plus FA cos psi divided by reluctance along Q axis. We will have to take vector sum of, because these two components are perpendicular to each other. So we will take vector sum of these two quantity and we will get the total armature flux. And this will depend on the power factor of load. The effect of power factor angle has already been incorporated in psi angle. So we will not use this relation, we will just say the armature flux is equal to armature flux, D axis armature flux plus Q axis armature flux. Now we will try to analyze these things with the help of phasor diagram. Let us say this is the direction of flux, field flux. So this will be the direction of induced EMF due to field flux, and since we are studying generator, so the terminal voltage will lag the resultant flux will lag the field flux. So the terminal voltage will lag the generated voltage. This is terminal voltage. Suppose we have a Salient type synchronous generator and some load is connected, some lagging load is connected. So some lagging load is connected at the terminal of generator. So the armature current will lag the terminal voltage. That is the meaning of lagging load. So let us say this is the armature current. and this is lagging with some angle theta, but psi, the psi we have to use in this relation, this is angle between EF and IA. So, this is the direction of IA. So, the psi will be angle between EF and IA, and we already know that the angle between VT and EF is called load angle, power angle or torque angle. So, psi is equal to, in all these relation we will have psi is equal to delta plus theta, where theta is the power factor angle of load, and this is internal power factor angle of load. So, in all these relation, at the place of psi, at the place of psi we will use delta plus theta. Here also we will use delta plus theta, and this is not required. Okay, so this is IA vector, and along the field, this is the field axis. Along this field we will have D axis, this is D axis, and perpendicular to this axis we will have Q axis. This is the direction of IA, and armature MMF is directly proportional to armature current. These two quantities are linearly related, maybe the number of turns. So, let us say the armature MMF is double of the armature current, or 1.5 times armature current. Let us say it is 1.5 times armature current. This is armature current and this is armature MMF. So, if this is armature MMF, there will be some D component, D axis component of armature MMF. So, this much MMF will be called FD, and the quadrature component will be now we need to calculate flux. So, flux along D axis will be phi D will be MMF along D axis divided by reluctance along D axis, and phi Q will be MMF along Q axis divided by reluctance along Q axis. Now, we know that the air gap along Q axis is very high as compared to, much more than as compared to air gap along D axis. So, let us say the reluctance along D axis is, so if air gap is high, reluctance will be high. So, let us say reluctance along D axis is equal to 1 unit. So, obviously reluctance along Q axis will be much more than 1 unit. Let us say it is 2 unit. So, to find out flux along D axis, we will divide MMF by 1. So, we will get the same length of flux, this is phi D, but in Q axis the flux is, the reluctance is 2 times. So, we will have to divide the MMF along Q axis by 2. So, along Q axis we will get half of the length of MMF. This is flux along Q axis. The resultant MMF is the vector sum of FD and FA. Similarly, the resultant flux will be vector sum of flux along Q axis and flux along D axis. Now, if you will take vector sum of D axis flux and Q axis flux, this is the addition point. So, this is the resultant flux, resultant, this is the resultant armature flux. Please observe that the direction of resultant armature flux and direction of resultant armature MMF is not same, because reluctance along the two axis is not same. If the reluctance along Q axis was also 1, the armature flux along q axis would be equal to mmf along q axis. So, the armature flux along q axis, the flux along q axis would be up to this much length. So, in that case, if you take the vector sum, the armature flux would be along the armature mmf. So, the two quantities are not in the same direction, and the reason for this is the reluctance along the two axes is not same. This is armature flux. So, in this way, if you know the power factor angle theta, you know the, if you know the delta, psi will be known, and if psi is known, we will have ID is equal to armature current sin delta plus theta, and IQ is equal to armature current into cos delta plus theta, and in this way we can calculate d axis flux and q axis flux, and if we will take vector sum, we will get the total armature flux. And here we have the phasor diagram for Salient type machine. Now, to make the circuit diagram, in the circuit diagram, the flux is modeled by a reactance. What we do, we analyze that the rate of change of flux, the effect of this flux is voltage, and voltage is directly proportional to the current which has generated this flux. So, the effect of this voltage, effect of this flux voltage is modeled as a reactance, and this voltage is equal to armature current into armature reactance. Like in cylindrical machine, we have modeled it like this. This is generated EMF, and here we have armature current, and this is armature reactance, and armature current into armature reactance is the voltage due to changing armature flux. JIA XAR is equal to voltage due to changing armature flux. But here we do not have, here first we calculate d axis flux and q axis flux. So, instead of one reactance, we will have two reactance in the circuit diagram. One reactance will be for d axis flux and other will be q axis flux, because the total armature flux is the function of power factor angle. So, we will make two different reactants. So, due to changing of d axis flux, there will be a voltage, and that voltage will be the effect of this flux. This is the effect. This will be directly proportional to magnitude of flux, and this magnitude of this flux is directly proportional to the current which has generated is. The cause of this flux is d axis current. So, this flux, this voltage will be directly proportional to ID, and this effect of this voltage, this will be directly proportional to IQ. So, to show the effect of this flux in the circuit diagram, or we will say the voltage due to d axis flux is equal to J, we will represent this reactance is a XDR into ID, and here voltage will be written as J XQR this is represented as XAD, armature reactance along d axis, and this is armature reactance along q axis, XAQ into IQ, and vector sum of these two voltages will represent the voltage due to total armature flux. So, if you take the vector sum, we will have J ID XAD plus J ID vector, because ID has a definite direction and IQ has different direction. This is J IQ XAQ. This is the effect of d axis flux and this is the effect of q axis flux. Here we will have IQ, and collectively both the effects are due to, this is due to armature flux, this is armature flux. So, where in cylindrical machine the armature effect is, the effect of armature is modeled into a single reactance. Here we will have voltage drop in two reactances, and in both the reactances currents are different. Here we have ID and IQ, and after this point we have generated voltage, and further if we will take the effect of leakage flux, then we will get terminal voltage. This is the effect of armature reaction. So, EF is written as, and this is the direction of IA, EF is written as Vt plus IA into XAR armature flux plus IA into leakage flux. This is due to leakage flux, and if we add, if we take JIA common, we will have XAR plus XL, and that is called synchronous reactance. In case of Salient machine, we will write EF is equal to Vt plus, if we want to take the total effect of armature reaction, we will have to take these two terms. We will write JIDXT, JIDXAT plus JIQ XAQ plus, this is the effect of armature reaction, and leakage flux is directly proportional to, the leakage flux has nothing to do with the orientation of rotor position, rotor. So, this will be directly proportional to armature current JIA XL. Obviously, armature resistance is neglected, RA is neglected. If RA is taken, so we will have IA into RA also. But I am sure in case of Salient machine, and in the most of the question which are asked in GATE, that armature resistance is neglected, whether it is synchronous machine or induction machine. In DC machine, armature resistance is not neglected. Okay. So, we have this relation. Now, this relation can further be modified, and if we make the circuit diagram for a Salient machine, we will have generated EMF, 1 voltage drop, JIDXT will represent JIDXT, then JIQXQ, then here we will have voltage drop JIA, JIA into XL, and here we will have Vt. But here I cannot show the, because all the voltages are added. So, I have shown these three components in series, but in other way connecting these three components in series will be wrong, because the same current is not flowing. In this winding I have shown armature current, in this winding I have shown Q axis of armature current, and here we have D axis of armature current. So, instead of drawing circuit diagram, I will just use this relationship. This relation can further be simplified as the IA vector. Here we have IA vector, because all the currents have some phasor, some direction. This IA can be further simplified as IA vector is equal to ID vector plus IQ vector. So, this is J ID plus IQ into XL. So, this is Vt plus, if you take JID and here also we have JID. So this will give you XAD plus XL plus JIQ into XAQ plus XL. So EF can be written as VT plus JID. We will write XAD plus XL is equal to simply XD plus, and this is written as XQ, JIQ XQ. So we have this relationship. So in this phasor diagram, the direction of ID is along D axis. This is IA. So I am going to draw a new phasor diagram, and that phasor diagram will be for this relationship. So in that phasor diagram, I will not show the MMF and flux. We will show let us say this is field flux and this is IF, EF, and at some angle we have VT here. This will be called torque angle, and let us say armature current is lagging. By what angle the armature current is lagging to the terminal voltage, it will depend upon the load, nature of load. This is angle theta, and this is D axis, and this is Q axis. Along the flux we will have D axis. So if this is armature current, this current is D axis current ID, we will write ID is equal to IA cos of this angle, and this angle is 90 minus delta plus theta. So this is cos 90 minus delta plus theta will be sin delta plus theta, and similarly the quadrature axis current IQ will be IQ is equal to IA cos delta plus theta. And from this relation, if you know VT, to get EF we will have to add JID into XD. Here we will have XQ, and if we compare XD and XQ, XD is equal to inductance along D axis into angular frequency, and this is inductance along Q axis into angular frequency, and inductance is inversely proportional to reluctance. This is inversely proportional to reluctance. So along D axis, if reluctance is low, air gap is low, so D axis reactance will be higher than Q axis reactance. Okay. This is the direction of ID. Then JID will be 90 degree anti-clockwise to ID. J will be 90 degree leading. So the direction of JID is along the direction of EF. Okay. And we have to multiply XD. So to get EF, we will add this vector. We will start this much vector from the tip of VT. So we will start from tip of VT, and we will add this vector will be JID into XD, and again in the summation of these two vectors we will add JIQ into XQ. The direction of IQ is along EF, so JIQ will be along phi f in the upward direction. So if we will add J I Q X Q, we will get E F. So we have to make the length of ID into XT such that if you add IQ into XQ, we will get EF. So this is the complete phasor diagram. If you draw a perpendicular from VT, in this phasor diagram RA is neglected. This length is VT sin delta. So VT sin delta is equal to this much length. This is equal to IQ into XQ, and this length is EF minus this length is VT cos delta. VT cos delta, this is equal to ID into XT. But this relation is not very useful for calculation purpose, because in the question I will take a typical question, and I will show that with the use of this relation that question will be difficult to solve. So we will have to manipulate this relation. So first I am taking the question. In the question, you will be given with the terminal voltage, and normally the generator is connected to reference bus. So at the reference, you know the magnitude of voltage, and angle is normally taken as 0. So suppose here the voltage is 1 angle 0. You will be given with all the information of synchronous machine. I mean, in cylindrical type machine, XS is given. So in salient type machine, you will be given with XD, XT is given, and X2 will also be given. And suppose a load is connected. So at the terminal end, you will be given with magnitude of armature current, and with the help of nature of load, you will also know the power factor angle. So at the terminal, you will be given with magnitude of armature current and its angle, theta will be given. So you have Vt angle 0, this quantity is given, and angle is also given, current and angle is given. If current is not given, then it will be given that instead of current, the power may also be given. So from power, suppose P is given, so P is equal to Vt Ia cos theta. So if power is given, nature of load is given, then Ia can be calculated. So suppose we are with this much information, and suppose question is asked to find out the magnitude of excitation voltage and the torque angle. So now you will try to use this relation. Vt is given, Xt is given, and Xq is also given, but Id and Iq is not given. And formula for Id is, then you will try to find out Id. The formula for Id is Ia sin delta plus theta. Ia is given, theta is given, but delta is not given. Even delta is asked to calculate. So if delta is not given, we cannot calculate Id, and if It is not calculated, we cannot calculate If. But if we count, we don't know the magnitude of EF, this is unknown, delta is unknown, we don't know Id, and we don't know Iq. We have 4 unknowns. We have 1, 2 equations, and this is a complex equation. So in the complex equation, with the help of real part or imaginary part, you can make 2 equations. So we have 2 equations here and 2 equations here. So in total we have 4 equations and 4 unknowns. So with the help of 4 equations, 4 unknowns can be calculated. But if we manipulate this relation, the calculation will be much easier. Generally, we will be given with armature current. So we will try to manipulate this relation. We will try to formulate this relation in terms of armature current. So EF can be written as Vt plus J I d x t plus J. IQ can be written as, the vector IQ can be written as IA vector, total armature current, minus dx is component of armature current into xq. Now EF vector is equal to Vt plus, from here I will take JIA xq common, means I will separate out JIA xq, and here we have JID xt and here minus JID xq. So this JID can be taken common, xd minus xq. Now in this relation we are given with Vt Ia with angle theta and xq also. So Vt is given, Ia with its angle is given, and xq is also given. So this vector can be calculated very easily, but in the complete calculation of EF, id is involved and id is unknown, and this is a function of delta, so delta is also unknown. So EF cannot be calculated even from this relation, but if you analyze this much relation, this can be calculated, and this quantity is called EF dash. EF is equal to EF dash plus J ID into XT minus XQ. Now let us say this vector is a vector. I am using the term vector because it has some magnitude and angle, and let us say this vector is collectively Vt plus Jia xq is some other vector B, and this vector is C. Now what is the direction of EF? EF is in this direction. This is delta angle from Vt, and what is the direction of JID into XT minus XQ? XT minus XQ is a scalar, so whatever is the direction of JID, we have to see the direction of JID. The direction of ID is downward, so the direction of JID will be along EF. So this is in the direction of EF, and the vector C, this is vector C, this is also in the direction of EF. We have three vectors, out of which two vectors are collinear. So from here B can be written as vector A minus vector C, and A and C vectors are collinear. A, this is EF, and JID is also in the direction of EF. So these two vectors are A and C vectors are collinear. So third vector will automatically in the direction of A and C. Suppose this is A vector and C is collinear with A, so C will be either in this direction or in this direction. So if you will take operation of vector summation or vector subtraction of A and C, you will again get vector either in this direction or in this direction, depending upon which has greater magnitude. So we can say that these three vectors are, if we have to take operation of three vectors and out of three, two vectors are collinear, then the third vector will also be collinear. So if these three vectors are collinear, this, and this, EF has angle delta, then EF dash, this will also have angle delta with respect to Vt, and this will also have angle delta with respect to Vt. Now if you see this EF dash is equal to Vt plus Jia xq, and in this relation all the quantities are known. So although we cannot use the whole relation to calculate EF, but with this much relation only we can calculate the direction of EF, or the angle of this much quantity, this will give you angle delta. And if you find out delta, With the calculation of delta only, IA is known, theta is known. So, ID and IQ can be very easily calculated, and once you know the value of ID, you know this value of this quantity. If you know the value of ID, the whole EF can be calculated, and delta is calculated even before the calculation of EF. So, you have the value of magnitude of EF, and delta is also known. So, EF is equal to EF vector is equal to Vt plus JIA xq plus JID into xd minus xq. This relation will be very useful in the calculation of Salient type synchronous machine. Since these three vectors are collinear, this is in the angle of delta, this is also in the direction of delta. So, after calculation of this quantity, you do not need to take the vector sum, because these vectors are collinear. So, you just calculate. After calculating this vector, you will know the value of delta, and after calculation of delta, you will know the value of xd. You just multiply xd into id into xd minus xq and add this term into the previously calculated this term. You will get the magnitude of EF. So, based on this formula, we will do numericals in different video lecture.